Welcome back to Conquering the JavaScript Interview, where with each episode, we dig deep, sift through the intricacies of JavaScript, and shed some light on the vital algorithms and data structures to empower you for that next big interview. Today, we're going to be diving in the world of binary search, a method so efficient that when it comes to finding elements, it rarely takes 2 tries. So are you ready to split your doubts in half and find the solution? Well, we're going to get searching here in just a second, but I want to remind y'all that to check the description down below for a link to our community membership. If you are interested in learning how to program beyond just these algorithms and data structures, if you want to learn how to build CRUD apps from scratch, then we have courses available for front-end, back-end development, which combined together make our full-stack program divided into 2 courses. We also have a standalone React course that I have made that takes you from 0 to hero, and I'm currently in the progress of making a TypeScript course that's going to be also expanding on the content we have in our full stack course. So if you have interest in joining all these courses, getting all these lectures and labs, and access to our Discord and our Discord community where you can ask questions and get personalized content and answers in real time, then click on that link, join up for $25 a month, and get involved. Otherwise, let's get back to searching. So while the origins of binary search are kind of hard to trace back, definitively, its concept has been around for forever. I mean, it's basically like taking something like guess a number between 1 and 100 and trying to find ways to reduce that subset of numbers to something more, to just reducing the range of possible guesses you could do of 1 to 100. You're going, well, I know this guy likes, middling to high numbers, so I'm going to eliminate 1 through 49 and just focus on 50 to 100, for example. Immediately, we can have the range of possible choices by making that kind of determination, whether it's knowing the person we're talking to or just playing 20 questions with our individual. The whole purpose is that's the idea of a binary search. Let's just have the possible range of the field and keep on searching for that number, right? It's a basically formal beginner's introduction into a lot of computer algorithms, and it dates back to the dawn of computing, right? And you're going to see binary searches as this foundational concept in all of computer science education and implementations and all this crazy stuff. So it's primarily used for searching for a specific element in a sorted list. Let me repeat that, a specific element in a sorted list. What it does is it repeatedly divides the search interval in half. If the value of the search key is less than the item in the middle of the interval, the search continues in the lower half. Otherwise, it just throws all that away and continues in the upper half. This continues until the value is found or the interval is empty. So we identify the middle element of the list. If it's the desired value, boom, we already have the index and we return that index. If the target is less, then we throw out the right half because we don't need to worry about it. And now we have half the field and repeat that process. Split it in half. If that's the index, go for it. Determine whether it's smaller or greater. So we basically take that quarter, ditch it, and go to the next, right? So if the value is greater than the middle element, repeat the search with the right half. If it's less, repeat the search with the left half. Basically taking each half we're repeating this with and having that down until we finally wind up with either the found value and its associated index, for example, in an array, or we return something like -1 or undefined or something that tells us that, hey, this value doesn't exist in this sorted list, right? So we return some indication that it's not present, and I'll be doing -1 in this one. So like I said, pros of binary search, it is very efficient, right? I'll talk more about its big O later, but it makes it pretty dang fast for large lists. It's very memory efficient, barring the implementation of it, depending on how we do that here. It uses a constant space, which means it doesn't require additional memory as the input list grows, and it's very predictable. If you're given a sorted list, the worst case and average case performance of binary search is always going to be logarithmic. Again, I'll cover more of that after the code implementation. It does have some cons that I've already talked about. For example, it's sorted list requirement. Binary search only works on sorted lists. If it's not sorted, you're either going to get incorrect results or have to sort it first, which can be computationally expensive. No frequency information either is a big one that you have to remember. If there are multiple occurrences of an element, binary search doesn't count them. It merely finds an occurrence. And it has variations implementation. Again, some don't consider that a con necessarily. Like people are like, well, I like the fact it can be implemented in a couple of different ways. But again, there are subtle ways to get binary search wrong, like handling rounding, off by 1 errors and things like that you can introduce into your code base if you're not careful. So with that in mind, let's just try not to dwell too much on this here and dive on into the code, right? So implement a binary search algorithm, nothing to it here. It's going to take two arguments, the input array, and you notice one is numbers that look like index positions. Trust me, when I'm trying to explain how this works, the index positions make it much easier to understand. And we have our target and our return value. So if we have an input array of numbers 0 to 9, not 1 to 10, because trust me, when we're talking about indexes on an input of an array of 1 to 10, it gets a lot more difficult to explain between index and value when they're both numbers. So I decided to make it a 0 to 9 array. If I have a target of 8, it should respond with the same thing as its index, which also happens to be 8. Again, that'll be easier to see when we actually get going with the code implementation here. Then we can also do strings, believe it or not. We can do an array of these capital letter strings of the first, looks like 20 letters of the alphabet, A through T. We have a target of H, which would be the 7th letter of the alphabet. So we're going to get or rather, its index will be the 7th if we count it 0. So it'll be 0, 1, 2, 3, 4, 5, 6, 7. And there's our index, the letter H right here. And if that's our target, that's what it should return. So again, it needs to find the index of whatever element we are searching for. And I'm going to say if it doesn't find it, return an index value of -1 from the algorithm. And that's it. So if I know those are my two arguments, let's go ahead and get started here. Oh, I should mention, I did say it works on strings, believe it or not, because JavaScript, like many other programming languages, compares strings based on their Unicode value of their characters. When the binary search code we're going to be writing here uses comparison operators like less than, greater than, or equal to with strict comparison, triple equal signs. On strings, it compares the Unicode or character code value of the string. So for English alphabet letters, the Unicode values are in ascending order from A to Z. So A is less than string B reports as true, right? Z is greater than A reports true, right? And it also gets kind of complicated when you have collections of letters. We're not going to get into that now, but know that we're going to leverage the fact it compares these Unicode values, and they also ascend from A to Z in that ascending order, which means that I can use these string values and compare them just fine. A little more JavaScript nuance if you weren't aware of it. So let's try and get going here. So there are two implementations I'm going to cover in this video. They're both going to be very similar. One is going to be an iterative approach, and you guessed it, if there's an iterative approach, there's a way to write it recursively as well. I'll discuss the pro and cons, the big O, and a little outro at the end. So our binary search is going to take two params. Sure. Let me center my keyboard on my desk here. Let's do a array and target as our two inputs. The array, the input array, no surprise there. The target or the target is what we're looking for in this array. 8, nothing to it, folks. Let's go ahead and just write the following, just because my console's all over the place. Let's write a call to our binary search function. And we're going to go ahead and do the first one here and try console logging some things along the way to see if it even helps us. So we're going to do my first example, an array of 0 to 9. If you want to follow along, you can always pause here and just like write it up yourself in whatever editor you're using, whether it's in browser or otherwise, so you can try and follow along or solve it. And then our target of 8. And because it returns nothing, we get undefined as our first console log. Hooray! Okay, but now that that's there, we can actually start working on visualizing how this works here. So remember, it's a whole divide and conquer, and splitting and having the whole thing is the idea behind binary search, hence all the puns in the intro of this video. So we need to know where our low point is, our high point is, and where our middle point is for these halves that we are working through as we throw out left and right halves as we begin searching through here. So we need to know a low point, which will start at the index value of 0. That makes sense. Our lowest value will be the start of the array, which will be 0 for all arrays. We're going to have our high point be our array length minus 1. So whatever our input array is, the last index position will be the length of the array, 10 elements in this case, minus 1, which gets us 9. So that's our high value, or our high index right now. Remember, we're not talking about indices, not values. So our low index is 0, our high index is 9, and there we go. Now we need to calculate a midpoint, but we need to calculate a new midpoint every time this thing runs. So I'm going to choose to make this variable scoped into our loop. Now, we don't know the number of iterations we might be going through here, so this is a great chance to teach students that, again, for loops aren't the end-all be-all of all iterations. You end up using while loops more and more in these kind of algorithm series because they are really good for an undetermined number of iterations. For loops are great for a set number of iterations, and while loops can continue for some indefinite amount of time, and that's what they're good for, and that's what we're going to use here today. So we're going to do an iteration here that says so long as our low value is less than or equal to our high value, keep on iterating, right? Because we have these two pointers here, as long as it's the low is not bigger than the high, we still have halves to be traversing, right? That's the whole point of the binary search. So yeah, that's what's going to happen here. Now, if this entire loop finishes and nothing from the while loop returns saying, aha, I found the index for you, like I said, this thing should return a value or some indicator that it's missing that index, aka in our case, we're going to ask it to return a -1. Okay. So what I'm going to do now is we need to write some conditions inside of our while loop, and we also need to calculate that midpoint like I was talking about. So let's go ahead and do that. Now, this is not going to be a variable we're reassigning anywhere in our code other than its initial calculation, so I know there's errors here, just bear with me. I have nodemon restarting my script here. We have this midpoint variable that we need to round down in this code's case. So we're going to grab our math floor function. We're going to take our low plus high, and we're going to divide that by 2 and round down, and that would calculate our midpoint for each iteration as this thing goes through. So what we're going to basically say here is, like I said in our steps, if the value at our midpoint is our target, then boom, we have already found it. So what I'm going to say is if our value at the midpoint is our target. So remember, the mid represents the index, array at mid is the value. If it is our target, then mid is our returned index, right? It represents the index position of the element that we are searching for, aka our target. So we're going to go ahead and return mid if we find it. Then we have two decisions to make, right? If the value at our midpoint is less than our target, we are going to move our low point up. If it is not less than our target, we're going to move our high point down. This is the determination of the splitting, right? Or the halving, the divide and conquer approach of binary search. We need to know, based on our midpoint, which half of this divided section are we throwing out. So if our midpoint, right, is less than our target, so if our target is, say, 8 and our midpoint has a value of like 5, then we know there's no point in searching 1 through 5 or something like that anymore, because those are all definitely less than 8. So we toss the whole left part of the algorithm out and move the low up to where the mid was, +1. And then we have a new half to search through. We determine the midpoint, determine where the value lies, ditch the right half or the left half. So this logic is how we determine ditching the left or right half of our search results. So we're going to say, if the value at our midpoint is less than the target, that means we're going to ditch the low half and take our low, which starts at 0, and move it up to where the mid was, +1. So that's what we're going to say is, low equals mid +1. Then the other case is we ditch the right half. So we take where our right pointer is and move it to where our mid was, -1 index position. So that's where we're going to take high and assign it of mid -1. And just like that, we get the correct answer right there, which is difficult to visualize, but nevertheless, it is correct. I don't know what to tell you. I mean, that's how it works. How about we console log and try and work our way through this step by step so we get it. As a recap on this code, I'm going to add some console logs here in just a second, and we're going to try and visualize how it actually got here, because it seems like some of these algorithms and data structures just seem like magic when you implement the code, because again, this is not that difficult, IMO, says a guy that's been coding for 6 to 7 years. But remember, the function starts by defining low and high pointers. They represent the range of elements to be considered, hence why on our initial iteration, it is the entire array, index 0, index length -1, aka our last index. The search continues as long as low is less than or equal to high. Again, once that low overlaps the high, we've searched through the entire possible ranges of the array and we have no choices left, hence why it will return -1 if it can't find that target. Let's test that. If I have a value of 10, which doesn't exist in this array, it should return -1, and it does. So, okay, we know that part now works with that little test we did there. Now, the midpoint is calculated using the average, hence why we do low plus high divided by 2, rounded down. If the element at the midpoint is the target, we have the index of our target, which means we return the mid, aka that's what this 8 is appearing right here, right? If the element in the midpoint is less than the target, the search continues to the right half of the array by updating low. So I said the low starts at 0, so we're going to say everything from our midpoint and behind is garbage, because there's no way those lower numbers can be 8, which means we throw that entire half away. Then we have the right half, and we move the index in 1 from where the mid was, because the mid wasn't it anyway, so there's no point in searching the mid again, which means we do mid plus 1, hence why we get that value. Then we do mid plus 1, we have a new low, the same high, calculate a new mid, and go on and go forth, right? Otherwise, the opposite logic of that is, okay, well, we throw away the right half and adjust the high inwards to where our mid is, -1, because everything behind that is not our answer. Because remember, we don't go to the mid, we do mid -1 or +1 because we already checked to see if that mid index did match with our desired target element, right? So that's why we do +1 and -1 on the midpoints, because we already determined the mid wasn't it. So if we ditch the left half, we go to mid +1. If we ditch the right half, we go to mid -1. Hence why that logic works out this way. The loop will basically continue until either we get our target and it returns the index of that target, or it finds nothing and returns -1, indicating to us, the programmer in this algorithm, that it didn't find that target. And that's it. Like I said, that's as simple as it needs to be. Let's see if we can add some stuff here to see how it works. So I'm going to do a new variable for visualization purposes called iteration. I'm going to console log the iteration variable. This might get nasty with these string concatenations here, but we'll see how it works. Okay, so I thought it would do. Would it not do 4 iterations on this value? No, it's 3 iterations. That does make sense, actually. Yeah, it's 3 iterations. Okay, sorry. Overthinking. So yeah, this should be solved in 3 iterations, and let's try and visualize these numbers, and I might grab out my a quick handy tool here to draw some stuff. So let's see if I can get this working here. All right. Cool. Let's see if I can get it working. All right, so what else do we need to console log here, folks? We should probably console log the low, the mid, and the high, as that makes sense for some things to console log. Now it's getting kind of nasty looking. Can I make it fit on one line? And then just so we know what this is logging, index of target plus the execution of our binary search. Now we have some more meaningful console logs here that aren't hopefully getting in our way and actually helping us, because I'm sure everyone out there is used to adding too many console logs, forgetting what they represent, at what stage and at what state of the function you're trying to log or whatever is going on here. Meaningful console logs, always fun. So what do we got? On iteration 1, we have a low of 0 and a high of 9. Those are our initialized values before any logic is fired. So the iteration 1, or initialization iteration, is a low of 0, the beginning of the array, an array of 9, that's the last index position, that corresponds with our input array. I'm going to take our input array up here and add it as a comment, basically, right? So we can visualize how this works. Okay, so boom. So our low is 0, which it happens to also be the element, but it's the index of 0 and 9. We haven't searched anything yet, so we have to search through the whole thing. Our midpoint is calculated of 0 plus 9, right? Which gets us 9 divided by 2 is 4.5. Rounded down gets us a mid of 4. So we go to 0, 1, 2, 3, 4. That is our current midpoint. So I guess we can, let's see if this works. We have our mid, we have our high, and we have our low. Okay, so we run through our logic. Is the array at the midpoint index of 4, which is also a value of 4, equal to our target value of 8? It is not. Therefore, we skip this if statement on the first iteration because it's not going to return our index position. So we then ask ourselves, is our array value at the midpoint, which is a 4, that's the value. Why did the thickness go bigger for some reason all of a sudden? Must have hit a hotkey that I'm not aware of. Perfect. Is it less than our target, which is 8, don't forget? No, that's a terrible 8. It is indeed less. So we're going to say that, okay, well, clearly everything to the left of this 4 is going to be less than 8. Because remember, we make the assumption this is sorted. So we throw all that crap out. The midpoint will get moved up to here. Or not the midpoint, the low will get moved up to here because it's mid plus 1. That'll become our new low. Let me go ahead and delete all that crap out of the way. Right, the low will go mid plus 1, and then the next iteration goes. So after that next iteration, that is what we see here. We know that all this has been tossed. The mid was 4. 4 plus 1 moves our low to the 5. The high has not changed. Right, so our low is still 5. Oh, you can't see my cursor. The low is indeed 5 index. High is still 9. That did not get changed. The new midpoint calculation is 5 plus 9 divided by 2 gets us 7, right? Because we get 14 divided by 2 gets us 7. So our new midpoint is the element, or the index, not the element, it happens to correspond to the element, the index of 7. So that's our new halves that we're looking through here. So we run the same logic. Is the value at the midpoint 7 equal to the target of 8? No, so it skips this, right? This is skipped still. Then we say, is our value at this midpoint 7 less than 8? It is. So what we do is, just like before, we remove all this crap out, and we move the low pointer up to where the midpoint was plus 1. That is when this next iteration occurs. And then we get a high of 9 still. The high has not changed yet. The low point got moved up to here because remember, we determined that everything from the first midpoint and behind was Garbo. Then we had this subset with the midpoint at 7 and below, we decided was Garbo. And then we have this calculation right here, which we get a low of 8, a high of 9. We see that over here. 9 plus 8 is 17. Divide by 2 is 8.5, rounded down to 8. So our midpoint happens to become 8. Then our array at midpoint value is 8, which is our target of 8. Therefore, we return 8 as our index position. And that right there is how this sucker works, folks. That's all there is to it. Beautiful. And that's it. That is how we can implement that right there. Let's see if it works as well with this array input of these letters. Let's see if it works correctly. So we're going to paste in my array of letters. I'm going to say look for a target of, I think H is what my input was. My target H, which should give us a return index of 7, which it does. And it's going to follow that exact same process that our input of the values did, right? So again, 0 in the first 20 letters, 0 to 19. A midpoint of 19 divided by 2 would be 9.5, rounded down to 9, hence that midpoint. Then we know that the midpoint will be, I believe, I or J at position 9. Then we know that H is less than J, right? So then we can ditch the full right half of all these letters. Those are all gone, and then we have one less than our midpoint of J onwards. So that becomes our new left half. The low didn't change, hence why it's 0 here. Then our high is 8, 0. Our low hasn't changed. 0, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so our high becomes 8. So 0 plus 8 divided by 2 is an even of 4. 0, 1, 2, 3, 4. And that becomes our midpoint. Then we ask ourselves, is our target... So unlike the previous example, we actually moved to the left half this time and moved our high down. And then what happens is... Oh, and I should have wrote 8, which is our high, not 8, it's our high. There we go. Right, and so we now have this subset. We have to determine which half to ditch. So we're looking for the target letter H. Our midpoint is E. Is E less than H? It is, so we can ditch E and everything before that, right? So then that leaves us with the following. Remember, the first half, that was our original midpoint right here. So we ditch everything below that is ditched from our first iteration, the 0, 9, 19. Then we got 0, 4, 8, which was this subsection. But we determined that everything, I think, E and before was Garbo. So that was going to be less than H. So we ditched all those. And that's why we're left with this subsection now, which got us, we moved the low point up to here. Our high point hasn't changed. And our midpoint calculation gets us G, 6. Yeah, that gets us our midpoint rounded down calculation. Is G less than H? It is, so we shrink it to the left once again. Hey, I can't erase single ones, what do you know? And then we are finally left with the last iteration, the 7, the 8, because again, that's our low, that's our high, that's a horrible H, folks, and the low happens to be also our mid that's calculated, they're the same letter, which is our value, which means a return an index of 7. So there you go. Like I said, there are going to be 2 implementations I'm going to show y'all here. I'm not going to go through all the crazy console logging madness again. We're going to call this binary search iterative. I'm going to go change my console log so it doesn't error out on me here. There we go. I'm going to try and implement this in a slightly different way. So now I'm going to have a function called binary search recursive. And it's going to take the same arguments, because there's not a whole lot of difference in the recursive. I mean, it has to work the same way iteratively as it does recursively, except we have to have just our recursive call, so that'll affect our arguments. And it will have to have an exit condition, just like our loop does. It'll be written slightly different. So we can say if. So not only are we going to be passing in our array in our target, we have to pass in a low value on each iterative call, or a recursive call, who will default to a value of 0, and a high, who will default to a value of array length -1. So this is how we're going to be passing in those parameters to, because they're going to have to know what low and high are to each recursive call. So we're going to say, so long as low is, in this case, greater than high, we're going, that means it's going to exit the recursion because, well, if the low got bigger than the high, we have finished dividing and conquering the array, never found a value, and we return -1 as the index. We have to do the same calculation for the midpoint in this case, so math floor of our average low-high, divide that by 2, and voila, there's our midpoint calculation. And here is basically where you can do something akin to the following. If the array midpoint is our target, we can say return our midpoint index position. Otherwise, we make an else if decision now to say, hey, let's change it up. Else if the array midpoint is less than the target, we do the same logic, which was our low point becomes mid +1. Well, what is our low? It is the third argument. So what we have to do is the following. Return another call to the recursive search with our new half. The same array, the same target, those are not going to change as the first 2 arguments. Our low is whatever our midpoint was +1, and whatever our high is has not changed. Then we can say otherwise, we return the other half of our recursive search if that happens to be the case, right? The low doesn't change, but the mid moves to in 1 where we toss that out here. But with that little change up here, I should be able to call this as well. Binary search recursive with a target of H, and we get indeed our target index of 7. So it does work the exact same way. If I console log the values of low, high, and mid, and the iteration count, or the recursive count, it would be the exact same value. It works the same way, just as a recursive style solution here. Now, in other videos, I haven't done this, but I'm going to take these 2 solutions and throw them into a CODEPEN so you can just have them and memorize them. That's what you got to do. Add your own comments and notes to it. But that about wraps it up for this video, right? So for real-world applications, Database and indexing, they use binary trees or other similar data structures that employ variants of these binary searches to quickly locate records. The Git version control system uses a method called dissecting that helps locate which commit introduced a bug, for example. Autocomplete and search bars and things like that begin suggesting completions. Binary search can be used in a lot of those things to find common search terms, quickly suggest matches. Computer graphics do a lot of binary searches. Gaming, obviously, that kind of ties into computer graphics. E-readers, if you're trying to search for a page and things like that, binary search is a quick way to locate the starting point of that section in a digital file. Page numbers are a list of numbers that are sorted. That sounds like a great use case for binary search. Oh, yes, big O complexity. I feel like I should probably talk about that. Now, both of these, let's see, I'll add a comment above each of these individually. So for binary search has a time complexity of big O of log n, like that. Not n log n, but just log n. And it has a space of big O of 1, because look at that, we only have a couple of variables, numbered variables here that aren't going to be growing particularly crazy. The time grows with the length of the array because that's more elements we have to traverse and have and split and divide and conquer. So the bigger the input array gets, the longer it gets, but it's not a linear, or it's not a, I'm trying to have a picture of this from previous times I've done these videos. Hey, so there's log n. Right? It's pretty dang good. It's a really efficient algorithm compared to even a linear algorithm of like n, for example. So yeah, it's very cool to know that its time and space is this good, right? Again, so irrespective of the size of the input, these numbered trackers of the pointers don't grow in size, right? And it doesn't utilize call stack like our recursive function does, hence why it's a big O of 1 space, and a time of, it's a logarithmic time because basically each iteration is half. So as the array gets bigger, it will take more iterations, but not nearly as many as like an O log or a big O of n, which is that linear diagonal line. The recursive solution is going to be the same time complexity. It has a big O of log n, and this one unfortunately has a slightly different big O space because it has the call stack issue. So the same time complexity, meaning the bigger the input gets, the more halves we got to do. But again, because we are halving, it's a log n and not like anything worse than that time complexity. The space, however, is also worse because in worst case, it's logarithmic. It's due to the recursive call stack, which can have at most log n entry calls stored in memory at any point in time, since the search space is halved with each recursive call. So both of their time complexities are awesome. This one clearly has a better space complexity. But again, I think it's cool to know how to write this and understand it because you need to get used to recursion. That's one of those really cool ways of answering interview questions to really show that you know your stuff. So you guys and gals and everyone else, thanks for watching. Hope you found this video useful in your journey to becoming a better developer. If you enjoyed it, consider giving us a thumbs up. Consider leaving a comment. Subscribing to our channel for more videos like this and look for this playlist. And remember, constructive and positive comments are how we all grow together. So thanks again for tuning in, and I'll see y'all in the next video.